Okay, so let's talk about binary trees. So as a starting point, binary trees are going to look something like this. Ooh. Maybe something kind of like that, where we have a node and that node has up to 2 children. All right, so we try to give some definition to it. So we have a binary tree. A binary tree has a root node. So now what's a root node? A node has a payload, just like we dealt with linked lists, right? So it holds a piece of information. And then it has a left child and a right child. And both of these guys are nodes. So we call this left child node, right child node. Now, a node does not have to have any children. So for instance, we go back to this picture. This node has no children. This node has no children. This node has no children. Make sense? Nodes without children are typically called leaf nodes. So think about this like a tree. Okay, when you see a tree, you have the trunk of the tree, then you have branches that come off of that, and at the very ends are the leaves, right? Nothing comes off the leaves. So that's like the outer outskirts of the tree are your leaves. All right, so these guys are called leaf nodes. Sometimes that's beneficial, sometimes that's not. Okay? All right, so now a binary tree plays by some rules. So we're going to actually put the rule at the node level. So actually, let's talk about the binary tree level, and then we'll put it at the node level when we write it. So a binary tree, everything to the left of the root node is less than or equal to the payload of the root node. Everything to the right of the root node is greater than the payload of the root node. All right, so if we fill this guy in a little bit, if we say that this is a 10, everything to the left of this is less than or equal to 10. So we might say this is a 9. We might say this is a 6. We might say this is a 6. We might say that this is a 7. And maybe this is a 13. So is it true that everything over here is less than or equal to 10? Yep. Is it true that everything over here is less than or equal to 9? Is it true that everything over here is less than or equal to 6? Is it true that everything over here is greater than 6? Is it true that everything over here is greater than 10? Make sense? So now when we go to add a node, so let's add I'm going to make this pretty specific. I'm going to add a 7. All right, so I drop the 7 onto the tree, top of the tree, right? I try to add it to the root. Well, the root's already taken, so it can't go there. So is a 7 less than or equal to 10, or is it greater than 10? Okay, it's less than or equal to 10. So 10 is going to ask his left child. Well, first he's going to say, do I have a left child? He does. So since he does have a left child, he's going to ask his left child to add the 7. All right, so 9's going to say, okay, is 7 less than or equal to me, or is 7 greater than me? 7 is less than or equal to 9. So then the 9 is going to say, do I have a left child? He does. He has a 6 as his left child. So since he has a left child, he's going to ask his left child to add the 7. All right. Is a 7 less than or equal to 6, or is it greater than 6? Greater than. So he's going to say, do I have a right child? He does. He has a right child. It's an 8. So he's going to ask his right child to add the 7. So his right child is going to say, is a 7 less than or equal to me, or is a 7 greater than me? Is a 7 less than or equal to 8, or is it greater than 8? Less than or equal to 8. So this 8 is going to say, do I have a left child? I don't. So make this guy my left child. Make sense? So that's how things get added. And what do we have here? We have, here's a node. A node has a left child. A node has a right child, as well as a payload. Here's a node. He has a left child that's this guy, and he has a right child that's null. Here's a node. He has a left child that's this guy. He has a right child that's this guy. Here's a node. He has a left child that's this guy. He has a right child that's null. This guy, even though we have to kind of spread it out a little bit, he has a left child and a right child that are both null. This guy has a left child and a right child that are both null. So trees, as they get bigger, if we want to depict them, gets a little bit sketchy because you need to kind of spread it out in order to show how things are related to each other. But that's just us visualizing it. All right, that makes sense? How a tree works in general? Okay. So let's open up our project. Which homework will this be? Are we sure? 5? The next homework will be homework 5. Okay. So I'm going to create a new project. We're going to call this guy CSC537 homework 5 template. All right, just use the minimum SDK, empty activity, and we'll start off with main activity name is the name of our main activity. All right, so we're going to go ahead. We're going to create a couple of Java classes now for our binary tree and for our node. Okay, so we'll right click here. We'll do new Java class. This is a plain Jane Java file, not something that's specific to Android. And we're going to create a binary tree class. And I'm going to create a second class here, new Java class. And this guy is going to be called a node. All right, and we've decided that nodes are going to have a private int payload. I'm going to use ints for our model because it makes it easiest for us to compare less than or equal to. We could certainly do it with strings and compare them like alphabetically, or another alternative is something called lexigraphically, but whatever, we'll use integers. They're easy to compare. So a node will have a payload. He's also going to have a private node left child and a private node right child. Now, what we have right here, doesn't that look pretty similar to what we wrote right here? So we designed it here, and then we made it a reality over here. Okay? All right, so now we need a constructor for this guy. So we'll have a public node, and this guy will take in an int payload. And we'll set this dot payload is equal to the payload that was passed in. And then we'll go ahead and set the left child equal to null and the right child equal to null. So a brand new node will have a payload, but won't have a left or a right child initially. Make sense? All right. Now we need to be able to get the payload, and we also need to be able to set and get the children. So let's go ahead and generate a getter for the payload, because we're going to be interested in what the payload of an individual node is, so I can compare it to my new node that I'm trying to add, right? So we'll generate a getter for payload. So there's my payload getter. And then I'm going to generate getters and setters for my left and my right child. All right, we go with node? All right, so any questions about that file? This is something we should all be able to do. We should all be able to create a file like that. All right. Using it might be a little bit more complex, right? We actually got to, put the rubber to the road. But the point is that if we sit here and we design our node to be this type of thing, you should be able to convert from this guy into an actual object that's capable of holding stuff. All right, so that's our node. Now let's go into our binary tree. And we decide if we look at our binary tree over here, we mentioned that a binary tree has a single node, which is the root node. And then they play by some rules, okay? So let's create our basic binary tree. So a binary tree is going to have a private node called root. We'll have a constructor. It'll take no parameters, and we'll say this dot root is equal to null. Now, we need to be able to add a node to my tree, right? So this guy will probably take in a payload, right? So we'll say public add. Well, maybe just called it add. Yeah, just call it add. This guy will take in an int payload. So we're adding something to the binary tree. And this guy is going to return nothing, so it's void. Now the very first thing we're going to do, we know that when we're adding something, a new node needs to be created. Correct? Regardless. So we're going to go ahead and say node, we'll say node n is equal to a new node. And nodes are built with payloads. Here's my constructor for node right here. He takes in an integer payload as a parameter, and he builds for me a node that has a payload equal to the payload I pass in, and has a left and a right child that are both null. All right, so that's what this guy will be. He will be a blank node that has no children. Now I need to add him to this tree. The trivial case is if, how do I say this? The easy case is if I don't currently have a root node. If this is the first node we're adding to the tree, he will be the root node, won't he? So how do I ask the question, do I currently have a root node? Or how do I ask the question, if I currently do not have a root node, make this guy my root node? How do I say that in Java? This is my root node, right? By default, he's going to be null. So I'm going to ask a question. So questions are always with an if. What's my Boolean expression? I want this Boolean expression to be true if I do not currently have a root node. So if what is true? This dot root is equal to null. So if my root node is currently null, then this dot root is equal to n. I'm a blank tree. You just wanted to add a 5. You are my new root node. If I didn't already have a root node, that new node we just created is my root node. Make sense? Otherwise, I need to ask my root node to add this node. So nodes need to know how to place things. If I'm in this else, we know that this dot root is a thing. It's not a vacant spot. It's not a parking spot we can take. All right, so I'm going to ask the root node to go ahead and appropriately add this node to the tree. Effectively, I'm passing the buck to the node. So we'll pause this here for a second. Let's go into node. So we're going to teach nodes how to add nodes to themselves. The rules of a binary tree are such that everything to the left of this node is less than or equal to it. Everything to the right of this node is greater than it. Now, if I'm in here, I know that I'm a parking spot that's already taken. I'm already a node. This guy can't have my spot, but I can try to put him as one of my children if I have an open spot. So I need to ask the question, is the guy that I'm trying to add, is his payload less than or equal to my payload? Or is his payload greater than my payload? If his payload is less than or equal to my payload, try to add to left child. Else, try to add to, well, let's just spell it out again. If his payload is greater than my payload, try to add to right child. Right? Those are the things we want to do. So I need to ask the question, if n's payload is greater than or equal, if n's payload is greater than me, try to add it to the right. If he's less than or equal to me, try to add it to the left. Doesn't matter which question we ask first, so maybe we say if n dot get payload. Now I'm actually going to ask a question here. So get payload, this guy's our getter for payload for a node, right? Payload is a private variable, correct? Why am I allowed to say n dot payload less than this dot payload? Actually, this should be less than or equal to. Why did I not have to use the get payload getter to get the value of that guy? Why was I able to get the value of n's payload directly when it's a private variable? What does it mean for a variable to be private? Available in the same class. I'm in the node class. It's a different node, but I'm still in the node class. So since I am in the node class, I'm technically in this is node class. But I have access to n's stuff directly if I want it, because I'm inside of the node class itself. Private only locks this variable down to being usable inside of the node class. Does that make sense? So we do not need to use the getter here. Now we could. It's not. We could either say n.payload or we could say n.getPayload. Choose your poison. This one is probably the easier to understand, because this is one of those situations where a private variable happens to work in a different way than you're expecting it to work, because usually when you make something private, it's because you don't want it to be accessible outside of that class, right? Well, because n is a node, I actually have access to n's private members because I'm currently inside of the node class. It's kind of a caveat to the rule. It follows the rule identically. It's just a situation we kind of didn't expect ourselves to be in. That's not why we made variables private. Make sense? So we showed it. You see how it works. You could do it that way if you wanted to. If you feel more comfortable not worrying about that caveat, you can always access this is private members. And then if you need to access another dude's private members, give yourself getters and just use them. Even though in this particular case, we didn't actually need a getter. We could have directly accessed it. Make sense? So nobody's going to be impressed if you take the shortcut, because I think it actually is maybe more difficult to read if you're not like very used to how it actually works, right? Like, oh, well, why can I say n.payload when it's private? If you're somebody who's been doing this a while and you look at, I'm in the node class, that's allowed. That's fine. But if it just looks weird to you, don't worry about it. Just call the getter and everybody's happy. Okay? So if n's payload is less than or equal to this is payload, then I'm going to try to add this to the left child. So the first thing I need to do is I'm going to say, well, do I already have a left child? If I have a vacancy, if there's an opening here, I can just make him my left child, and I'm done. So I can say if this dot left child is equal to null. If I don't have a left child, then I can say this dot left child is equal to n. And I'm done. I don't have one. Welcome aboard. You're now my left child. Otherwise, so this says, if I don't have a left child, set n to be my left child. If we're in here, I already have a left child. So ask my left child to find a home for n. So we'll say this dot left child dot add n. Because my left child is a node. Nodes have a function called add that take a node as a parameter, so we'll ask our left child to call his version of the add method. Does that make sense? So that's what I do if this guy should go to my left. Otherwise, he should go to my right. So if I don't have a right child, set n to be my right child. So if this dot right child is equal to null, this dot right child is equal to n. Now for you right now, this would be a pretty good habit to get into. Spelling out what you want to do in English before you actually write it in Java. Eventually it's going to get annoying because you're like, okay, well, this is actually easier to write than this big, long, stupid sentence. But until you're used to doing it, till you're used to that translation, right, then it helps to kind of sit down and write it out. So would you agree that that and this ask the same thing? All right, so get used to writing those, and then you'll get very confident with that. You won't have to write it down first. So otherwise, I already have a right child. So ask my right child to find a home for n. This dot right child dot add n. And eventually this guy's going to find a home as he trickles down through my tree until he finally gets to an empty parking spot. Make sense? So we built all of that into Node. So a node knows how to add another node to themselves, following the binary tree rules. These are those binary tree rules. So all we have to do at the binary tree level is we say, look, if I have an empty tree, this guy's my new root node. Otherwise, I know the root is a thing. This dot root dot add n. Tell my root node to add the new guy. And then he'll do the thing. Make sense? So not a whole lot of code to do it, but very important code. Now, what's kind of interesting about this code? So first of all, binary tree is quite simple, isn't it? Most of our mechanics are housed inside of Node. We would call them, it's encapsulated inside of Node. That gets back to 535 when we talk about the difference between procedural programming and object-oriented programming. I usually use the example of the telephone, where you have the big pile of wires as the procedural telephone. Something that looks like a telephone is the object version of a telephone. So root is a node, right? Now, when we're in here, we just use this telephone like it's no big deal. This root dot add n. If we peek under the hood, we see there's a bunch of wires in here. That make sense? So all of our details are sitting here inside of Node. We can get to them if we need to, but once we have it set and working, we just throw it into an object. And then we can conveniently use that object right here. Because we know that this guy might have to call a roots add method 15 or 20 times, maybe even more, until it finally finds a home for n. But from our perspective here, we're delegating. I'm passing the buck. So I'm the binary tree. I say, I already have a root node right here. Add this guy. I'll go back. Because now it's his job. Does that make sense? All right, so that's what we've written here. Okay. Now, what are some things that would be handy for us to have in a binary tree? Do we want to know maybe how many elements we've added to the tree? So maybe we have a count. Private int count. And when a tree is first created, what's the count going to start off as? 0. There's nothing in the tree. Every single time we call add, what will the count go to? 1 bigger than it used to be. Because we know in here, one way or another, that dude's getting added. Right? He's either going to be trivially added right here, because he's my first root node, or my only root node, or I'm sure my root node will take care of the dirty work for me. So I can actually just assume I have one more node right here at this level. So keeping track of the number of elements in my tree is pretty easy. Okay, so let's go ahead and give ourselves a getter for that count then as well. So I'll right click. I'm going to generate a getter for count. That way we can publicly get that guy. Okay, so what we're going to do here is we're going to build a little interface for adding stuff to our binary tree. This is going to be in our activity main guy here. So we'll go ahead and dump the hello world. We'll go ahead and throw our vertical linear layout in here. And then let's give ourselves a little edit text at the top for putting a number into. Well, here, I'll just put plain text. We'll click on this guy. I'm going to change his input type to number. It can actually be a signed number. That should be fine, because it can be positive or negative. we're going to put the hint for enter number to add. Take the current text out, and then let's center that. And then we want to go ahead and give ourselves a button that when we click that button, it adds this to our binary tree, right? So we'll throw a button in here, and we'll say add to tree. All right, and then let's go ahead and let's throw a label in here, or a text field, or text view in here that always shows the number of elements that are currently in my tree. Okay, so what we're going to do is we'll put that underneath here. Now, what I'm actually going to do, just so I can kind of label it, I'm going to take a layout. I'm going to do a horizontal layout here. I'm going to put that horizontal layout right here. I'm going to throw my text view into that guy. And then I'm going to create a second one in there. So I have two right next to each other. This first one, I'm going to have his text say number of elements, like that. And I'm going to right justify it. The second one is where the number is going to actually live. Now, so I'm going to call this guy num elements TV. That'll be his ID. And initially, we'll just set it to 0. Now, we probably want to have a little spacing between those guys, right? Like not just have number of elements and then 0 right next to each other. Now I could fake it by coming here and maybe throwing a couple spaces there between them. You could do it, and that's probably even just as correct as what I'm going to show you. But as an alternative, I'll go ahead and take those extra spaces off there. So now they're mushed together again. I'm going to go to my linear layout guy here, and let me close this. I'm going to do view all properties. I'm going to add some padding. I'm going to do padding to the right. And let's do, oh, that's actually I think that's where I want to have it. No, that's not where I want to have it. Padding end. I want to do padding between. Padding to the right added padding here. So this is for the linear layout. Okay, so what I need to do is I need to actually, I go to the text view and I can add padding on the right of like 2. And that gives me some space. So I'll just make it 4. So it effectively was equivalent to me putting the spaces. So I just took this text view and I said, make him seem 4 pixels wider than he actually is. And that gave me a little bit of gap. That way I can always, now I just need programmatic access to this guy right here called num elements TV for him to hold the current number of elements. And just for us to test that, I'm going to actually start the text off at -1. Okay? Because we'll go ahead and initially set this text view's count equal to our binary trees count. So we should get a 0 out of it. Okay. So let's go ahead and let's do the onCreate on this guy. And we're going to need programmatic access to this guy too. So this guy's going to be input ET. So we're going to need access to this guy, and then a function for this button working. Okay. Let's go back into our main activity. Up top here, I'm going to create some private variables. So private edit text, input ET, and then I'll have a private text view. What did I call that guy? Count TV. I just want to name it the same as I called it in here. Num elements TV. Okay. And then we're going to go ahead and programmatically grab those guys. So this is going to be get our widgets from our layout. So we'll say this dot input ET is equal to the edit text version of this dot find view by ID r dot ID dot input ET. So that'll grab the edit text. And then this dot num elements TV is equal to the text view version of this dot find view by ID r dot ID dot num elements TV. Now, why am I turning it into either edit text or a text view here? Why do I have to do that? Why can't I just leave that off? What do you think? Why is that? Why would that be a problem? So I'm looking at just this line here. What does find view by ID return? It returns a generic view. I'm trying to store this view inside of num elements TV, which is actually a text view. Now we happen to know that r.id.num elements TV is a text view because we're the ones who created it, right? It's going to find it as a generic view. So we can go ahead and say he's actually a text view. So go ahead and convert him into that for us so that I can store him inside of this container. Make sense? So this is pretty much how it's always going to look because find view by ID always gives us a generic view because it's just looking for something by its identifier. Okay, so now we have access to those two guys. We're going to go ahead and now we're also going to build for us a binary tree using our tools that we created. So we'll say private binary tree BT. So we'll create our binary tree. So we'll say this dot BT is equal to a new binary tree. And then just to test it, we'll go ahead and say this dot num elements TV dot set text. Now this dot bt dot get count is going to give me an integer. Set text requires a string. How do I convert this integer into a string? For example, if I have a 5, how do I make it a 5? Can't ask easier questions than these. What nice simple trick do we have with Java that allows us to turn anything into a string? Empty string. I can just concatenate that guy onto the empty string, and now it'll be a string. So the empty string concatenated with the 5 will give you the string 5. That make sense? This is another thing. These are things that you need to know. All right, promise you that on the final exam, we're going to have 10 questions. One of the questions is going to have you do something like this. It would be a shame for you to lose 10% on the exam because of something so easy as that. Make sense? There's plenty of hard problems, so don't lose your points on those. Don't lose your points on something trivial. Okay, so we have our new binary tree, and then we'll go ahead and we'll just set our, proving ourselves that we have the access to the label, we'll set that label equal to whatever our count was. Okay, and initially we had it at -1, right? I put a -1 in here as the starting point. And let me, I'm gonna make this text larger here. Let's make it 24. Let's make it 18. Will that fit? There we go. And then we'll make this guy 18. All right, so initially we have this at -1. So we should see when we run this, it should turn into a 0 because we have an empty binary tree. All right, so there's my 0. Okay, so now we need to have a way to read in this number, and we want to read in the number when we click this Add to Tree button. So we'll go into main activity. We'll create our function for making that button work. So we're going to have a public void add to tree button pressed, and this guy will take a view v as a parameter. All right, and what's he going to do? Well, you could probably ask the question to make sure there's a number there. So we can say if this dot input et dot get text dot length is greater than 0. So as long as there's something there, let's grab the value, and the value is going to come in as a string. So I need to convert a string to an int. How do I do that? That one's less easy. We need a special tool, the parse int, that lives in the integer class. So we'll go ahead and say int num, actually let's call it payload, is going to be equal to integer.parseInt, and the string we're going to be parsing is from this.inputEt.getText.toString. That'll get me the numeric version of the string that is in that edit text. And I'm storing it inside of a variable here called payload. Now, once I have that, I need to add that guy to my tree. This dot bt dot add, and add takes in a payload. So I'll pass it my payload that I just read in. And then I'm going to write a little function here called private void update tree count. All right, and all this guy is going to do is he's going to update the current count for the tree. So I'm going to move this line here. I will just put that in that function, and then whenever I need to do that, we'll call that function. So we'll initially do it up here, this dot update tree count. And then again, after I've added something to my tree, I'll say this dot update tree count. Okay. So now we should be able to go in. We need to hook our button up to this event. And now we should be able to add stuff, and we should see that our count goes up. There's my button. Go to its on click. Here's add tree button, add to tree button pressed. Click that guy. Have I shown you toasts before? Like a little error message? All right, so yeah, one thing you could do is you could say, do a toast that says you must enter a number or something like that, but we won't waste our time doing it right now. All right, so we'll try to add a 5, add to tree. We have one element in there. I'll add an 8, add to tree. We got another element in there. So that would have gone to the right. We'll add a 1, add to the tree. We got another element in there that went to the left. Let's add another one, another one, another one. Doesn't seem to be crashing, so our adds seemingly are working. So those are our number of elements that have been added to the tree. All right, so now we need a way of visualizing our tree. That make sense? Okay, we need to be able to visualize our tree. So we have a couple of different ways we can visualize trees. So here's my tree here as an example. So we could say in order, pre-order, post order. All right, so these are the different ways we could visit our tree. In order, pre-order, and post order. So let's look at how in order works. In order says, let's create some slides for these. Says visit the, let's say visit in the following order. Left child, yourself, right child. That's in order traversal. And let me show you what that means. So if we're doing this tree and we're visiting it in order, the first thing we visit is our left child. Then we visit that guy's left child. Then we visit that guy's left child. So the first thing that, so in order traversal of this guy will be a 6, followed by, then we visit ourselves, which is this 6. Then we visit our right child. We visit his left child first, so that's the 7. Then we visit ourselves. Then we visit his right child. There is no right child. Bounce back up. Now we visit the 9. We're visiting ourself from this perspective. Then visiting his right child, which is nothing. Then bounce back up. Now we visit the 10. And then we visit his right child, which is, and he has no left child, so we visit ourselves, which is a 13. That's in order traversal of that tree. See how that worked? So this guy says, I need to visit my left node first. Then he says, I need to visit my left node first. Then he says, I need to visit my left node first. Then he says, I need to visit my left node first. I have no left node.
8 has to be first.
Huh?
And the node 8 after 6, 8 has to be. I didn't understand how.
Yeah, let me do it again then. So let's just go through this. A visit, when I say visit the left node, then the right, the visit the left node, then yourself, then the right node, that's happening on a per node basis. So when I first start off and I'm taking this entire tree as an example, I'm saying, here's my node. Visit yourself in order. He says, okay. So the first thing I'm going to do from this guy's perspective is he's going to visit his left child. Okay, so now we're at this guy's perspective. The first thing he does from his perspective is he visits his left child. Now we're at this guy's perspective. The first thing he does from his perspective is he visits his left child. Now we're at this guy's perspective. The first thing he does from his perspective is he visits his left child, and he has no left child. So then what does he do? He visits himself. So we first visited this 6. So this very first 6 here was this 6. Now we bounce back up. Now we're back to this guy's perspective. So what's the first thing he did was visited his left child. We've already done that. The next thing he does is he visits himself. So the second 6 here is this one. That's him visiting himself. Then the third thing he does is he visits his right child. Now, from the right child's perspective, the first thing he does is visit his left child. Okay, these are all from the perspectives of an individual node. So the first thing this guy does is he visits his left child. The first thing this guy does is he visits his left child. He has no left child. The second thing he does is he visits himself. That's where the 7 came from. Then he visits his right child. He has no right child. So now we're done here. We bounce back up. The second thing this guy does is visit himself because he's already visited his left child. So now he visits himself. There's the 8. Then he visits his right child. There is no right child. So he bounces back up. This guy's now done. Bounces back up. This guy now visits himself because he's already visited his left child. So there's the 9. Then he visits his right child. There is none. So he's done. Bounce back up. This guy now visits himself because he's already visited the left child. So visiting himself is a 10. Then he visits his right child. Now we're at this perspective. The right child says, visit the left child first. He has no left child. Then he says, okay, now visit myself. There's the 13. Then he says, okay, now visit the right child, which is none. We're done. That's in order traversal. Make sense? Pre-order. We visit ourself, then we visit the left child, then we visit the right child. That's pre-order. We visit ourselves first before we do anything else. So ourself, then left child, then right child. So a pre-order, from 10's perspective, the first thing we do is we visit 10. Oop. So this guy visits himself, then he visits his left child. Left child then visits, from his perspective, visits himself. Then he visits his left child. His left child visits himself, then visits his left child. He visits himself, then tries to visit his left child, there is none. Then he tries to visit his right child, there is none. So now we bounce back up. He visits his right child. He visits himself first, so there's our 8. Then he visits his left child. There's our 7. He tries to visit his left child, there is none. Tries to visit his right child, there is none. Bounces back up, tries to visit his right child, there is none. Bounces back up, tries to visit his right child, there is none. Bounces back up, tries to visit his right child. There's our 13. Make sense? Post order. Says visit ourselves last. So left child, then right child, then ourselves. So for post order, from 10's perspective, we're going to visit the left, we're going to visit the left, we're going to visit the left. Try to visit the left, can't. Try to visit the right, can't. Then we visit ourselves, so that's our first 6. Bounce back up. Now we'll go to the right. We still haven't visited this other 6 yet, so we went to the right. Try to visit the left. Try to visit the left, can't. Try to visit the right, can't. Visit ourselves. There's our 7. Bounce back up, try to visit the right, can't, visit ourselves. Bounce back up, try to visit the right, can't, visit ourselves. Bounce back up, try to visit the right, try to visit the left, can't, try to visit the right, can't, visit ourselves. Bounce back up, finally visit ourselves.
Accidentally summon me.
I did. That's a good question. We did so it's not here, visit here, that's the 6. Visit the 7, visit the 8, then it's the 6 after that. So we finally do the 6 before we bounce back up here. And try to visit the right, then we get the 9. Try to visit the right, left, right, finally get here, then we visit the 10. So that's post order. Make sense? All right. So what we're going to do is in our homework, give this as a starting point. Actually, I'll go ahead and throw a linear layout in here. So why don't we go ahead and we'll throw a scroll view. Where's my scroll view? Is it a widget? Is it a layout? Container? It's a container. All right, so here's my scroll view, and he has a vertical linear layout in it. And I'll go ahead and kind of want him at the top. So I'm going to say match parent there. Okay, that's not going to actually help anything though. That's fine. Why did I put it so far down? Oh, it's because my horizontal linear layout is set to match parent for height. I want it to wrap content for height. There we go. So now there's my scroll view, and here's my linear layout. So what we're going to do is we're going to add 3 buttons here. So right below we need a layout first. It's going to be after that button. We're going to do a horizontal layout. And then we're going to throw a button in there. That'll say in order, pre-order, post order. And we'll have the height of this guy. We'll wrap content. Okay. So now when you click the in order button, it's going to empty out the our scroll view, or the linear layout that's in here. So maybe call this guy output view group starting point. And what he should do is he should fill up this output view group with individual text views in the order in which we visited those for in order visiting. So if you click in order for this particular, our example back here, it should fill up that thing at the bottom with a text view that says 6, then another text view that says 6, then another text view that says 7, then another text view that says 8, then 9, then 10, then 13. So 7 individual text views, similar to what we did with like the Towers of Hanoi. Make sense? Then if I go back and I hit a different button, if I hit pre-order, then it should empty out what's in here, visit my tree again in the pre-order way, showing me all the things we visited pre-order one text view at a time, filling up this scroll view. Make sense? So your homework assignment is to implement the functionality for these 3 buttons and have it fill up this piece down here.
Could you do one for example?
Oh, I'm not going to do it because if I do one, then all the other ones will be easy. You've seen how these work, right? In order, pre-order, post-order. So visiting them should be fairly easy. And once you have one of them figured out, the other 2 will be trivial. Because there's only 3 steps, right? Question is, do I visit myself first, or the left child first, or the right child first? Make sense? So once you get it done once, the other 2 will be easy.
If you give the numbers, it should show the order, right?
Correct. If you had built this tree, if you used our interface to build this tree, it would, and you click the in order button, it would show a 6, then a 6, then a 7, then an 8, then a 9, then a 10, then a 13. If you used our thing to build this exact tree.
And the way we enter the numbers.
Yeah.
Order of that.
Yeah, would create this tree. If you enter the order, the numbers, and it would generate this tree, that's the order it should generate. That makes sense? So you're making 3 buttons work. So I'll go ahead and I will, let me actually stop the recording.